All right, so particle motion worksheet 2, or no, worksheet 1, number 2. And remember, you don't need to turn in both particle motion worksheets, just one of them, because they're the same stuff, just more practice. By the way, the ones that have a number beside them, a year beside them, like worksheet 2, a couple of them have a year next to it. It's because these are old AP test questions. We started sort of giving credit to the year. Number 2. X of t equals t over 1 plus t squared for t greater than 0, where t is in seconds and x is in meters. All right, find the velocity at time t and at t equals 2 seconds. So how do I find the velocity? Derivative. So, quotient rule, f prime is 1, g prime is 2t. So that's not terrible as far as quotient rules go, I guess. So gf prime minus fg prime all over g squared. Oh, I wrote that down wrong. There we go. So 1 minus t squared over 1 plus t squared squared. Could that be simplified? I don't think so. I think we're good. Plus, we don't have to simplify anyway, so leave it alone. And at time equals 2, so what will I do for time equals 2? Plug in 2 for t. So 1 minus 2 squared over 1 plus 2 squared squared. And that would be a safe stop. Right? That's nothing wrong with that answer. 1 minus 4 is 3. 1 plus 4 is 5. Squared is 25 meters per second squared. Part B. When is the particle at rest? Right, left, justify your answers. Let's justify first.
Meters per second squared.
Whoops. Thank you.
Acceleration.
Meters per second. So what am I looking for? When is it at rest? How will I know?
V is equal to 0.
V is 0. How about moving to the right?
V is greater than 0.
And then V is less than 0. So there's my justification from the get-go. Now I kind of know what I'm looking for. So let's find the rest first. And then then I can set up the number line. Actually, I could put this on the calculator as well and figure out where it's positive and negative. What makes a fraction 0? The top or the bottom?
Top.
Just the top. So I'm not really worried about the bottom. So t equals plus or minus 1. Sort of. Well, can't have negative time, and they explicitly told me that at the beginning. T's got to be greater than 0. So I don't have to worry about negative 1. So t equals 1. So at t equals 1, it's at rest.
Now we can take some volunteers.
We can do one of two things. We can do the number line with volunteers, or we could put this in the calculator and just look and see where it's positive and negative.
I like the calculator idea.
Plus, the calculator idea will hopefully confirm that the velocity is 0 when t is 1. Let's see. fraction bar, 1 minus x squared, 1 plus x squared, whoops, squared. There we go. 1 minus x squared over 1 plus x squared squared.
Positive from -1 to 1.
And I don't really know what x's and y's will work, but we'll just try that. Good enough. Ooh. I'm going to say not good enough. I want a better y window to look at.
You know, it's negatives, but it just gets smaller and smaller.
Zoom in a little bit here. Okay. Close enough. Or good enough to see what's going on.
Looks cool.
So you can say this from the graph, since you have a calculator. V is greater than 0 from 0 to 1. And we can include 0 because at 0 we have a positive velocity. And I guess we should.
T is
should.
greater than or equal to this 0.
Let's explicitly answer the question, though. We're moving right. When v is greater than 0, that happens between 0 and 1. And we're moving left when v is less than 0, and that happens from 1 to infinity. Wait, yeah, here's a question. How do I know it's 1 to infinity? I don't see all the way out there. How do I know it doesn't go positive somewhere else?
Because it gets lower.
Do you want logic?
I mean,
Because I said so.
Would you like logic?
I want you to tell me why it doesn't. How do I know it doesn't go positive anywhere else?
Okay, so if you square a negative, it's going to be positive, and 1 plus a positive is always going to be positive. But then if you have a negative,
You're too far in the weeds on this problem. There's only one place where it's 0. So if it's continuous, so assuming this graph doesn't jump around, which I think we can say based on this, there's no holes or asymptotes. For it to go positive again, it would have to go through 0. But we only have one place where it's at rest. So no other places does it rest, so it can't cross back into the positives. Question on any of that? Part C. Find the displacement of the particle from 0 to 4. Find the displacement of the particle on 0 to 4. So that's S of 4 minus S of 0. That's what displacement is. So S of 4 is 4 over 1 plus 4 squared. In fact, if we really wanted to be lazy, we could just leave it like that. Minus S of 0.
Which 0 over anything is 0.
Yep, 0 over 1 plus 0 squared. And you could leave that as an answer. I mean, it's not simplified, but it doesn't have to be simplified. 4/17 minus 0 is 4/17. Since it's with calculator, you could do a decimal, but you could also leave 4/17. .235. So, like, all of those are acceptable answers. Part D. Find the total distance traveled by the particle between 0 and 4. Okay, well, something happened at 1, so I need to be real careful about 1 second. I'm going to draw the motion diagram. Like, you can get this answer without the motion diagram, but I think the motion diagram is helpful to see what's going on. So I already know my endpoints. Displacement is just the difference between those two. But distance means I need to account for the fact that if we, ran back and forth a couple times. So what number do I need to worry about between 0 and 4? And why? 1. And why 1? That's when it's at rest. That's when it changes directions. So I need S of 1. So it starts at 0. It moves to the right for 1 second. I'm trying to verify that with what I said already. Moving right from 0 to 1. That gets us to 1/2. T equals 1. And then it moves around or changes directions. And from 1 second to 4 seconds, it's moving to the left. And at 4 seconds, it's at 4/17, which is somewhere between 0 and 1/2. That's good enough. Somewhere between 0 and 1/2. Note, graph not to scale. And it keeps going that way.
Just inching.
Yeah, it's slowly going that way.
It's not inching, just centimeter into a meter.
So total distance then, from 0 to 4 would be, let's see, traveled 1/2.
1/2 minus.
And then, we just do that. 1/2 minus 4/17. Right? Why risk messing up fractions? Traveled 1/2, that was from 0 to 1. And then from 1 to 4, we went from 1/2 to 4/17. But I don't want to mess up. It's not even that I worry about messing it up. I just don't want to do it. Yeah, that's my safe stop. That's distance. It's a calculator problem. So I could put it in the calculator. What's that? 1 minus 4/17. 0.765. But why even mess it up in the calculator? Unless it specifically says, well, it does say, give decimal answers correct at 3 decimal places. So I guess we should do that. But you got a calculator, so we're not worried about messing things up.
Acceleration.
Find the acceleration of the particle. Because what does it take for acceleration?
Not quotient rule again.
V was 1 minus t squared.
Over 1 plus t squared squared.
So yes, I get to do quotient rule again, and this time a little bit harder quotient rule. That's not bad. F prime isn't bad. G prime.
Chain rule.
Chain rule or algebra, but I think chain rule. Something squared would be 2 times the something to the first.
1 plus t squared times.
And then times 2t. Chain rule. This is going to be ugly, but that's okay.
GF prime minus FG prime.
GF prime minus all of that. 4t, 1 plus t squared, 1 minus t squared. Maybe that simplifies. Maybe I don't want to mess with it. 1 plus t squared. Squared, or to the fourth. Do a little bit of algebra. Find the acceleration of the particle at time t.
No, we did that.
And at time 3. I have a shortcut for time 3. Because my calculator can do derivatives.
Wait, what?
it can do specific derivatives. It can't do symbolic derivatives. That'd be nice. But it can evaluate, if I'll put in what velocity is, which I did, then I can take the derivative, as long as 3 is in my window.
No.
It is now. I can get my calculator to find the derivative. Second calc, dy dx, at x equals 3, 0.036. And I guess if I really wanted to check my work, what could I do?
You could actually solve the problem.
Yeah, I could put 3 in for t and all of that stuff, and I should get 0.036. If I don't, then I did something wrong.
With the acceleration, no.
And then lastly, speeding up and slowing down.
Well, it's speeding up at 3, so that's good.
I don't want to.
No.
I don't want to. Let's do it this way. Let's just kind of review that. Let's look at our possibilities here.
Right really small.
Yeah, writing really small is pretty nice solution.
There we go. There's our. It's all about their signs. If they're both positive, that's the easiest one.
Speeding up.
Speeding up. If velocity is positive and acceleration is negative, slowing down.
Signs are same, they're speeding up. Signs are opposite, slowing down.
So what about V is negative, A is negative?
They're speeding up because of the double negative. That double negative.
Kinda, yeah. You're going backwards and you're going faster backwards, or you're going more backwards, or however you want to phrase that.
Backwards squared.
And then the last case is, this is the one that's tricky because you see A is greater than 0. You're like, oh, acceleration's positive, we're speeding up. No, it means your velocity is getting greater, but it was negative, and so it's going
Getting
from
closer.
negative 10 to negative 8 to negative 6.
Let's say it's getting closer to 0.
So you're slowing down. This would be when you're in reverse in your car, backing out of the driveway. You hit the brake, which gives you a positive acceleration,
T
which
equals
seems
3.
weird.
That's a good example. Because
What's a good
when
example?
So when T is, if you go back to the graph,
Okay.
T is 3, and we said, and it is negative, velocity is negative, but when we took the derivative, it's positive. That's
So what's happening? Oh, we are slowing down. And I think we can see that in the graph. At time equals 3, our velocity is negative, but it's getting closer to 0, so we're slowing down. Even a better picture there.
Yeah.
20 minutes on that problem.